always had a slight disagreement. He always thought I was a little too conservative. You know, he would like to say, I really want to see if we can cure cancer. And I said, that's a great idea, but cancer can hide on you. Cancer can be tough to cure. I don't know if we're going to cure cancer, folks. I'm not going to say that. I am going to say I think we're going to treat it effectively with this, and we have a better chance of curing it with treatments like this. But ultimately, I'm a researcher. I have to have it proved to me. So that means that once I treat a patient with any treatment, an operation, a drug, John's device, I'm going to want to see them surviving many years before I'll start throwing the cure word out. I do think that's possible. Now, what makes John's device so unique and what makes this a great potential? Well, here we get back into my background in chemistry, and I did some work at Los Alamos National Labs in New Mexico many years ago. So I knew a lot about electromagnetic radiation, radio waves, other things. But I also knew a lot about chemistry, and I had started working with these tiny little particles called nanoparticles. And nanoparticles truly are so small you can't see them oftentimes. And so we've got things in scale there. So you can see I'm about 6 feet tall, so a 6 foot tall person is about 2 million nanometers tall. So, excuse me, 2 billion nanometers tall. You know, a human hair is about 75,000 nanometers in width. So these are tiny, tiny particles. Well, how do you visualize that? How do you really think about that? Well, I like to put things into scale. Well, this is Reliant Stadium, where the Houston Texans occasionally play football, occasionally play something we don't recognize. We're hoping for a winning season, but we'll see. So everybody's been to a stadium, right? Some kind of a big football stadium, or you've gone to a college game, big stadium. So 75,000 people. Well, imagine that stadium is a cancer cell. How many nanoparticles could we put into that? Well, imagine either that soccer ball or that golf ball. About the biggest particles I'm using would be the equivalent of filling Reliant Stadium with soccer balls, the smallest one golf balls. You literally can get billions within these cells. So we're talking about things that are so tiny that you could just pack them into the cells. The beauty is we don't have to get that many into the cells, but it gives you an idea of the scale we're talking about. Very, very tiny particles into these cells. This is John's genius, these white towers you see there. The black machine in the middle is the radio wave generator, the radio frequency generator. These are fairly standard pieces of equipment. The towers that you see there are the field generating devices. And this is where his design ideas and where his ingenuity really came to bear. He realized he could build a high voltage generator station there that would give you an ability to treat. Now, the things that I asked him to do was to kind of make it more of a standing wave, and we made some modifications talking on the phone. And as I said, when I first talked to him, I knew a lot about the theory behind this, but I certainly didn't have his ability to build, design, and visualize. And so he had that ability, and he built exactly what I asked. And this is what we're now using in the lab. Importantly, this equipment has been great in the lab. It allows me to treat cancer cells. It allows me to treat animals with tumors. It's not really big enough to treat a human. We're in the process of working on designing and engineering a human-sized device now. The Rutkowski family will be doing all of that work here in Erie. And ultimately, they and I will go down to the FDA, hopefully sometime later this year, early in 2010, and show them the design diagrams, because that is what we'll need. We will need their sign-off on a human-sized device before we can even think about proceeding with human trials. Again, a little bit about electromagnetic radiation. This is something that John and I talked about all the time, and we made changes. We're all surrounded by radio waves all the time. Radio waves, television waves. I mean, again, you can see sort of the frequency there. People think when we say electromagnetic radiation, they worry about ionizing radiation, which is X-rays. We use radiation therapy to treat patients. Radiation is damaging. The beauty of the wavelengths that we're using, which are down here in the, if you see there where it says between the 1 and the 10 megahertz, we're in that general range. So RF welders, radio, TV, those are the kind of frequencies we're using. So the difference here is that it is a very focused, very powerful wave. And John knew that if you had something metallic or semiconducting in the cells, it could release heat. So the fact that we're getting bombarded by radio waves, we all know that that doesn't harm us, that doesn't hurt us. We also know from some research done by the United States Air Force that if you treat human beings with a high power radio wave, now if you leave them there for an hour or two, they start getting a little bit sweaty. But once again, it doesn't do damage. There's already been a lot of work done with these sorts of waves that have been shown to not be harmful or damaging to humans, so we don't even have to repeat that work. It's already been done. So John was one component of this. The other component was another patient at MD Anderson, Professor Richard Smalley. Professor Smalley and I had started talking about doing some work with nanoparticles about the same time that John contacted me. And so as I thought about this, I went to Professor Smalley and said, gee, I'd really like some of your carbon nanoparticles to try in this radio wave field. And he politely told me, well, it's not going to work. Nanoparticles are so small, these waves are so long. And he and I had a very polite argument in his room one day, and I explained why I thought it would work, and he accused me of being a very strange surgeon thinking about things like this, to which I said, thank you very much. I consider myself a very strange surgeon. But he finally, in one of those sort of, go away son, you're bothering me moments, said, okay, I'll give you some nanotubes, so go test them. And of course, when I tested them and they heated, he was amazed. Now, unfortunately, Professor Smalley, like John, suffered from leukemia, and he and I designed a series of experiments over the last few months of his life. I'm sorry to say he died in October 2005 from leukemia. Importantly, this is a man who won the Nobel Prize for finding these nanoparticles. 2 days before he died, I was sitting with him in his hospital room, and he looked at me and said, you have to continue this work. This is probably going to be the most important thing I've ever done. So he saw John's vision. He saw the importance of it, and he and John actually had several conversations about this. So they shared a drive, they shared a belief that this could really be life-changing in terms of our approach. So what are these things that we're talking about? This is an example of a carbon nanoparticle called a single-wall carbon nanotube. These things are very tiny. They're only about a nanometer in diameter, about 100 to 200 nanometers long. They have a lot of potential purposes, not just medical. They're being used for electronics. They're being used in engineering. They actually are incredibly strong. These nanotubes are stronger than anything else that's ever been measured or designed before, stronger than any steel. It's being used for construction. It's being used to strengthen products, make them lighter, et cetera, et cetera. We were interested in their properties